Hello, listeners. So, welcome back to our lecture videos. So, in the past video, we've looked at how we derived two expressions of the Joule-Thomson coefficient and proved that the Joule-Thomson coefficient for an ideal gas is zero. So, in this video, we're going to look up how we can mathematically derive again an expression for Joule-Thomson for a real gases. And at the end of this video, we will look at its implications at high temperatures and low temperatures. Okay, to start off with, we have this van der Waals equation of state, which is one of the many models that describes the behavior of a real gas. And hopefully in this lecture tutorial, we will try to derive the Joule-Thomson coefficient of this van der Waals equation is just equal to this one. To start off our derivations, we should remember the Joule-Thomson coefficient is given by this equation, which tells us the change in temperature accompanying a change in pressure at constant enthalpy. In calculus, we have the cyclic rule, which is a formula that relates the partial derivatives of three interdependent variables, let's say x, y, and z. Here, the subscripts indicate which variables are held constant when the partial derivatives is taken. So if we apply this rule, the Joule-Thomson equation is expanded into the following expression. If we try to isolate the delta T over delta P at constant H on the left side of the equation, then we will have the following expression. Now, I hope you noticed that the term is actually, the denominator is actually equal to our heat capacity at constant pressure, or Cp. Rearranging this equation would give us then this following expression. So let's leave this equation for the meantime, and later we will use this in the succeeding derivations. Alright, so we will use this same thermodynamic relationship that we've used in the previous video, and if we apply the reciprocal rule to the right-hand term of this equation, we will end up with this expression. So again, we'll try to leave this equation for the meantime and use this for our succeeding derivations. Now, for real gases, we have this van der Waals equation of state, and you're all familiar with this one at this point. Now, if we isolate or get an expression for temperature, we should be able to derive this expression. Starting from this equation, we can get the partial derivative of temperature with respect to volume at constant pressure. To do this, we will treat this term here as a constant, and we will just take the derivative of the terms inside this bracket. Now, I have listed the important derivatives for you in the left side, and we can use the product rule. Now, it is important that you should spend some time to use these derivatives and convince yourselves that we will have these terms in our final equation. Now, if we distribute this term to V minus NB, then we will have the following expression. We can also express the last term P plus AN squared over V into nRT over V minus NV. We can derive this easily from our van der Waals equation. So finally, we have three terms inside the bracket, and we are now ready for the next steps of our derivation. Alright, so the dependence of van der Waals constants A and B on enthalpy are additive as shown in this equation. Now, to evaluate this equation, there are three things that we need to do. First is to set A, or the attractive term, to 0, and we compute or derive the dependence of enthalpy and pressure. Second is to set B, or the repulsion term, to 0 and compute how the enthalpy depend on pressure. Then finally, we can add the derived values together. We can now start if we set A equal to 0 and see how does the enthalpy depend on pressure in the van der Waals equation. If A becomes very small, then these terms in the equation becomes negligible. After cancelling the constants n and r, this would lead us to a more simplified equation that is t divided by v minus nv. Now let's use this equation that we've derived earlier. Substituting delta t over delta v at constant p for t over v minus nv will give us the following equation. We can then cancel out temperature term, and apparently the volume term will also cancel out. Overall, this gives us the enthalpy dependence on pressure simply equal to NB. Now, what does this tell us? If the attraction term A is 0, then the enthalpy dependence on pressure is simply equal to NB at a given temperature condition. Okay, so the next thing for us is to evaluate the equation and see how the enthalpy change if B, or the repulsion term, becomes very small. Again, this is the van der Waals equation that we've derived earlier. Now, if B becomes a very small value, then the following terms will be negligible. These terms will be 0, and this will give us the following equation. Just like what we did earlier, we use this expression and substitute this to the enthalpy dependence on pressure equation. Now, this expression looks a little bit messy at this point, so we have to simplify this to give us this expression. Again, you can pause this video and try to work out the mathematical operations involved in this derivation. We can further simplify this equation if we can take out 1 over v in the denominator. Doing this will lead to the following expression. Okay, so it's your turn to show how I was able to simplify this equation into the following expression. Okay, so we'll start with this in the next slide. Okay, this term here in this equation is very small, and I will use this an approximation. I will approximate that this 1 in the numerator as 1 minus 2an over RTV squared. Again, this part here is much smaller than 2an over RTV. That's why we can do this approximation. Now, this term, 1 minus x squared divided by 1 minus x, is simply 1 plus x. Okay, so simplifying this equation leads to negative 2an over RT. At this point, okay, I've tried to summarize the steps, and you can do some algebra to show the complete steps of the derivation. Alright, so we have this expression to calculate the dependence of enthalpy on the constants A and B. We can now simply add them as shown in this equation. So we put them together and we will have this equation for the enthalpy dependence on pressure, which is simply NB minus 2an over RT. Recall from the cyclic rule, we were able to generate an expression to calculate for delta T over delta P at constant enthalpy as follows. Substituting the values that we've derived earlier will yield the following equation. Alright, so finally, with the Joule-Thomson expression for a real gas using the van der Waals equation of state is just simply equal to 1 over Cp times 2an over RT minus B. Now, take note that we've derived this expression and this is only applicable under low pressure conditions. Alright, so after all that effort that we've put for the derivation, what is the significance of this Joule-Thomson equation for a real gas? Now, let us try to interpret this equation into two extremes. That is, at very low temperatures and very high temperatures. Okay, so let's see what happens to the Joule-Thomson coefficient when the temperature gets very low. That is, what is the limit when temperature goes to 0? Well, as temperature goes to 0, all terms with T in the denominator gets very large. So the term involving 2A over RT gets much larger than B. And B term can be neglected at very low temperatures. Clearly, the equation will give a positive value for the Joule-Thomson coefficient, and this actually agrees with the experiment. Now, a positive Joule-Thomson coefficient means cooling, but also we have to take note that the resulting expression contains only the van der Waals constant A. So this means that the terms involving B are gone at very low temperatures. Lastly, we can also look at what happens when temperature gets very large. This result is quite simple since all terms in our equation containing the temperature in the denominator goes to 0. And the net result is negative B over Cp. And this is very interesting. First, it agrees with the experiment since it is a negative, meaning it involves heating. And secondly, notice that all terms involving van der Waals constant A have now vanished, leaving only B, or the repulsion term.